In this video, we are going to learn how to change the order of double integrals. So, taking a type 1 region, changing it to a type 2 region, or a type 2 region, going to a type 1 region. Our motivation for doing so could be to simplify the region, or it could be based on the function that we are trying to integrate, and we'll see a few examples of each. Starting with the region, sketch the region of integration and change the order of integration. So the double integral they gave us is the double integral of the function f of xy dy dx, where the y bounds go from 0 to the natural log of x. So these are the y bounds, and the x bounds go from 1 to e. So we're not doing any integrating here. We just have a generalized function, f of xy. We're focused solely on changing the order of integration. So we want to instead integrate in the order dx dy. And that's going to require us changing this type 1 region into a type 2 region. So let's focus on that now. So first thing, let's draw the two curves that bound this region. So y equals 0, so that's just the x-axis. So we have x and y. And then we have y equals the natural log of x. So if this is 1, natural log of x, going to look like this. So y equals the natural log of x. And then x goes from 1, so the intercept, the x-intercept, to e. So call that e. There's our region in here. And again, it's defined as a type 1 region where we draw the lines vertically throughout the region. Now we want to define this as a type 2 region. So we want to go from left to right. So on the left, we are bound by y equals natural log of x, but we need to redefine this as an x equals equation. So if we take y equals natural log of x, and we exponentiate both sides base e, we have e to the y equals x. So we can now start to set up our new double integral. Same function, f of xy, new order, so dx dy. So on the left side, we're bound by e to the y. On the right side, we're bound by e, so x goes from e to the y to e. And then y moves vertically from 0 to this point here, which is the natural log of e, which is 1. So from 0 to 1. So really it's all about the region of integration and switching from type 1 in this case to a type 2 region. Allows us to change the order of integration and we're good. Now, the motivation for this one is integrating with a natural log of x bound will probably lead to an integration by parts. Not that we completely avoid it when the bound is e to the y, but the integration by parts, if it does come up, will probably be a little bit easier with e to the y as opposed to natural log of x. Right, so just giving some motivation of why we might go through this process. All right, another one where we're just focused on the region. So double integral of the function f of xy still, dx dy, where our x bounds, so x goes from arc sine of y to pi over 2, and y goes from 0 to 1. So now we are starting with a type 2 region that we want to convert to a type 1 region to redefine the order of integration. Motivation here, we don't really want to integrate with an arc sine of y bound. Who knows what this function is? Maybe there is a simple function that arc sine would work nicely in, but for the most part, we want to avoid integrating with an arc sine bound. So let's sketch our region. So we have our x and our y. So x equals arc sine of y. So that will probably be easier to think of as y equals sine of x. Although we do have to include the domain restriction. Arc sine of y means y or x rather, is only going to go from negative pi over 2 to pi over 2. So if this is pi over 2, our sine curve would stop there for the arc sine. It would go through to negative pi over 2. We don't need that part based on this region, okay, but that's where it would go to. Right, so it stops there. So x goes from arc sine of y to pi over 2. So I'll draw that vertical line to create the boundary. See if I can draw it a little better. Okay, so we're going from arc sine of y to pi over 2, left to right. And on the y-axis, we're going from 0 to 1, which makes sense. 1 is the maximum value of sine curve. So again, this is x equals arc sine of y, which we've already redefined. If we put this as a y equals equation, we would take sine of both sides. So sine x equals y. So setting up our double integral now as a type 1 region, we want to draw our lines vertically in the region. So y is going to go from 0 to sine of x, from 0 to sine of x, and x is going to go from 0 to pi over 2. So there we have the order changed. Okay? And for the most part, I think these bounds would be considered simpler than a bound with arc sine in. So now that we focus on the region, let's complete the problem where we actually do integration out. So evaluate by reversing the order of integration. So in this example, the motivation for changing is because integrating e to the x to the fourth with respect to x would be very difficult, if not impossible, the way that it sits. If you honestly wanted to try to do it, you would probably need a Taylor series substitution here, which for most students, when they hear Taylor series, they want to avoid that at all costs. But let's look at changing the order of integration and see what happens to this problem. Okay, so dx dy means our region is type 2, so these are x bounds, these are y bounds. We'll draw some axes, so x and y. So x goes from the cube root of y to 1. For graphing purposes, probably easier for us to think about this as y equals x cubed. So y equals x cubed. All right, we'll go that way. And then to 1. So we'll call that 1. So x goes from cube root of y to 1. So we're drawing horizontal lines in our region. And again, we're starting out calling this x equals the cube root of y. This would be x equals 1. And that point of intersection right there, when x is 1, y is 1. So there's our region, everything filled in on our graph. Now we want to define this as a type 1 region. So we want to draw our lines vertically now. So we've already rewrote that. So this would be y equals x cubed now. So redefining our double integral, we have the double integral of e to the x to the fourth dy dx, where y goes from 0 to x cubed, and x goes from 0 to 1. Now integrating with respect to y, much simpler. There is no y in the function, so we just get the integral from 0 to 1 of y e to the x to the fourth evaluated from 0 to x cubed dx. So we get the integral from 0 to 1 of x cubed e to the x to the fourth, and then minus 0, and then dx. Let me rewrite that forward just so it looks a little bit cleaner. Okay, so now we need to integrate. So underline x to the fourth, that would be our u in a traditional u substitution. Du would be 4x cubed, so we need a 4, which means we'll also divide by 4. So circle the 4x cubed, that would be your du if you were doing the u substitution out. So this is going to be 1/4 e to the x to the fourth, right? Think about integrating e to the u, just e to the u as the integral. And we're going to evaluate that from 0 to 1. So we get 1/4. I'll factor out the 1/4. So if we plug in 1, e to the first is e, and then plug in 0, e to the 0 would be 1. So 1/4 times e minus 1. Much simpler to integrate dy dx than it would have been to integrate dx dy. Slash impossible, in a sense, to integrate with respect to dx first. One last example, just to finish this out, evaluate by reversing the order of integration. We have the double integral of the square root of 1 minus y squared dy dx, and y bounds go from x to 1, and x bounds go from 0 to 1. So this would be a great opportunity to pause the video, try this on your own, see how you're processing everything, and then play the video and see how you do. Okay, so hopefully you paused it and gave this a shot on your own. I haven't finished the problem. I set up the region. You can see in red what it would look like as a type 1 region, the way it's defined, and then blue going left to right. Make sure you define the correct region. This is the triangle above the line y equals x, not below, because y is going from x to 1. So you start your vertical lines on x and go up, and then x goes from 0 to 1. And then redefining now as a type 2 region, we have the double integral square root of 1 minus y squared still, dx dy. And now x is going from 0 to y, and y is going from 0 to 1. So integrating with respect to x becomes much easier. There are no x's in the function, so we just get 0 to 1, x square root of 1 minus y squared. Evaluate that from 0 to y dy. So integral from 0 to 1 of y square root of 1 minus y squared dy. At this point we can integrate. So if we were to do a u substitution, u would be 1 minus y squared. du would be negative 2y. So negative 2. Put a negative 2 to adjust. So think of integrating u to the 1/2 power if you're doing a traditional u substitution. So that's going to give us negative 1/2. And then 1 minus y squared to the 3/2 times 2/3. We're going to evaluate that from 0 to 1. So we get negative 1/3. We'll factor that out. So then if we plug in 1, we get 1 minus 1, so 0. So 0 minus, if we plug in 0, we get 1 to the 3/2, which is 1. So multiplying out, we get positive 1/3. And again, what was a very challenging problem in the order that they gave us becomes a much simpler problem. Now, the level of difficulty here can change if the directions prompt you to change the order, or if they just tell you to evaluate and you need to recognize that you need to change the order. So that's something to look out for. It's a way to make these problems a little bit more challenging, where the recognition is put on you to pick up on the fact that you need to go through this process of changing the order of integration to make the integration simpler. Other times, they will directly tell you, change the order of integration and then evaluate. Okay, so just something to pay attention to as you look through directions and go through practice problems. See you in the next video.